Policy as Code Unlocked, your comprehensive guide to open policy, Agent OPA. Chapter 1, The Digital Rulebook, Why Policies Matter More Than Ever. Every day, countless decisions are made across our digital world. Who can access what? What action is permitted? How do we ensure these choices are consistent, secure, and compliant? As our technological landscape becomes increasingly vast and interconnected, spanning cloud services, microservices, containers, and serverless functions, the challenge of managing these crucial decisions escalates dramatically. Imagine a bustling, ever-expanding digital city. In this metropolis, new buildings applications are constantly being erected, new roads, network connections, laid, and millions of citizens, users, automated systems, go about their daily tasks. For this city to function, it needs rules. Without them, chaos reigns. These rules in the digital realm are what we call policies. Policies are the unseen digital infrastructure that dictates behavior, grants or revokes permissions, and ensures order. They are fundamental to security. This is often the first thing people think of. Policies dictate who can access what data, when, and how. They define user permissions, data encryption requirements, and network access rules. For example, a policy might state, only authorized administrators can delete production databases. Compliance. In many industries, stringent regulations, like GDPR for data privacy, HIPAA for healthcare, or PCI DSS for payment card data, mandate specific technical controls. Policies ensure your systems adhere to these requirements, making your operations auditable and legally sound. A compliance policy might mandate all sensitive customer data access must be logged for a minimum of 7 years. Governance. Beyond strict security and compliance, internal governance policies ensure that digital operations align with organizational best practices and strategic goals. This could involve rules about infrastructure configuration, resource tagging in the cloud, or how data flows between services. An example, all Kubernetes pods must have resource limits defined to prevent resource exhaustion. Operational control. Policies can dictate how resources are allocated, how requests are routed, or even how systems respond to specific events. For instance, a policy might ensure that high-priority customer requests are always routed to dedicated server instances. For years, organizations have managed these policies through a mix of methods, each with significant drawbacks in our current complex environments. Hard-coding policy logic. Often, policy rules are simply embedded directly within application code. This works for simple, static rules, but if a policy needs to change, every application relying on that rule must be updated, retested, and redeployed. This makes policy management slow, error-prone, and inconsistent across different services. It's like having every building in our digital city write its own unique fire escape rules. Manual processes and human review. Many organizations still rely on human review boards, spreadsheets, or lengthy documentation to enforce policies. This is inherently slow, unscalable, and susceptible to human error. It creates bottlenecks, slows down development, and can lead to policy violations going unnoticed until it's too late. Imagine a human police officer at every single intersection, making traffic rules on the fly. Coarse-grained identity and access management, IAM. Traditional IAM systems, like role-based access control, or RBAC, are excellent at defining who you are and assigning broad roles, e.g., admin, viewer. However, they struggle with fine-grained, contextual policies. Can John view this document if it's outside business hours and he's not on the engineering team and the document itself is sensitive? Such complex, conditional logic often falls outside the scope of traditional IAM, leading to either overly permissive access or significant manual overhead. The limitations of these traditional approaches become glaringly obvious in today's dynamic, distributed digital city. Hard-coded rules create fragility, manual processes stifle innovation, and coarse-grained permissions lead to security gaps. What's needed is a better way, a unified, flexible, and automated approach to managing policy. This is where Open Policy Agent, OPA, steps in. Think of OPA as the highly efficient Department of Digital Rules and Decisions for our digital city. Instead of every building having its own rulebook or human officers manually enforcing rules, this central department handles all decision-making. Here's how it generally works. When any part of your digital city, an application, a cloud service, a Kubernetes cluster, an API gateway, needs a decision, is this user allowed to open this file? Can this new server be deployed? Should this transaction be approved? It doesn't try to figure it out itself. Instead, it sends a request to OPA. This request contains all the relevant facts and context for the decision. For instance, if an application wants to know if Alice can access document X, the application asks OPA for a decision, providing details like user, Alice resource document X, action, read, and perhaps even time of day, 3 a.m. OPA then takes this request, called an input, consults its meticulously crafted and version-controlled rulebooks, which are your policies written in a specialized language called Rego, and combines them with any up-to-date factbooks, external data, like a list of banned IP addresses or the current weather. After evaluating all this information, OPA returns a clear, unambiguous decision. Most commonly, this decision comes back as simple JSON data, for example, allow, true or allowed, false, reason, access denied, outside business hours. Crucially, OPA doesn't enforce the decision directly. OPA is a decision engine. It tells you what the policy dictates. The system that originally made the request is then responsible for enforcing that decision. If OPA responds with allow, false, the requesting application might then block the user's access, or the cloud deployment tool might prevent the server from launching. This decoupling of decision-making from decision enforcement is a core concept that provides immense flexibility. With OPA, organizations like large financial institutions can move away from manual compliance checks across thousands of applications and cloud resources. Instead of slow deployments and missed vulnerabilities, they can automate checks early in the development pipeline and at runtime. By integrating OPA, they ensure consistent security and compliance without human bottlenecks. Developers receive immediate feedback, accelerating their work while bolstering the institution's overall security posture. In essence, OPA offers a unified way to manage, distribute, and enforce policies across your entire technology stack. It transforms policy from an abstract guideline or hard-coded logic into a dynamic, auditable, and scalable component of your digital operations. This shift in thinking, treating policies as programmable, testable, and version-controlled assets, much like application code itself, is fundamental to navigating the complexities of the modern digital enterprise. This paradigm, known as policy as code, is not merely a technical change, but a cultural one, empowering organizations with greater agility, security, and control. In the next chapter, we will dive deeper into this transformative concept and explore why policy as code has become an indispensable practice in our digital world. Chapter 2: Policy as Code. The Paradigm Shift. In the previous chapter, we explored the critical role policies play in our increasingly complex digital world and identified the shortcomings of traditional policy management approaches. We briefly introduced Open Policy Agent, OPA, as a powerful decision engine designed to address these challenges. Now, let's delve deeper into the fundamental concept that OPA champions and enables: policy as code, PAC. Imagine our bustling digital city again. If Chapter 1 highlighted the chaotic, inconsistent rules emerging from individual buildings, Chapter 2 introduces the city planning department's master blueprint. This isn't just a set of abstract guidelines. It's a precisely drawn, version-controlled, and executable set of schematics for all city operations. These blueprints define zoning laws, building codes, traffic rules, and public safety regulations. Any new construction or modification must conform to this single, official blueprint, ensuring consistency and order across the entire city. This master blueprint is a perfect analogy for policy as code. At its heart, PAC is the practice of managing and automating policies using software development principles and tools. It means treating policies, rules, and governance as executable software definitions rather than human-interpreted documents or hard-coded application logic. Let's break down the key characteristics of policy as code. Externalized and decoupled. Policies are no longer embedded within applications or infrastructure configurations. Instead, they live separately, often in dedicated policy repositories. This means the rules can change without requiring code deployments or infrastructure reconfigurations. Declarative. Instead of writing step-by-step instructions on how to enforce a policy, which is known as imperative programming, PAC defines what the policy is, the desired state or outcome. For instance, a policy doesn't say check user's role, then check document sensitivity, then check time of day, then allow deny. Instead, it simply declares the conditions under which access is allowed, e.g., access is allowed if the user is an admin and the document is not classified, top secret, and it's within business hours. This simplifies policy expression and evaluation. Machine-readable and executable. Policies are written in specific, machine-readable languages, like Rego, OPA's policy language, allowing them to be automatically evaluated by policy engines like OPA. This eliminates human interpretation errors and ensures consistent enforcement. Version-controlled. Just like application code, PAC policies are stored in version control systems, such as Git. This provides a complete audit trail of every change, who made it, and when. It allows for collaboration, peer review, easy rollback to previous versions, and prevents policy drift, where policies in different environments slowly diverge, leading to inconsistencies and vulnerabilities. Testable. Because policies are code, they can be rigorously tested. You can write unit tests for your policies to ensure they behave exactly as expected under various scenarios and inputs. This significantly reduces the risk of policy errors or unintended consequences. Automated deployment and enforcement. Policies are deployed and applied through automated pipelines, similar to continuous integration, continuous delivery, or CI/CD, pipelines used for software. Once deployed, they are automatically enforced by policy engines like OPA at runtime, whether for authorization decisions, infrastructure validations, or compliance checks. Why is policy as code a paradigm shift? The benefits of embracing policy as code are transformative for organizations operating in today's cloud-native, agile environments. Consistency across environments. PAC ensures that the same rules apply uniformly across development, staging, and production environments, and across different services or applications. This eliminates the "it worked on my machine" problem for policy, reducing configuration errors and improving reliability. Increased agility and speed. Manual policy reviews and traditional change management are slow. With PAC, policy updates can be as fast as code deployments. This allows organizations to respond rapidly to new security threats, compliance requirements, or business logic changes without manually reconfiguring systems or redeploying entire applications. This means faster time to market for new features that integrate policy requirements seamlessly. Enhanced visibility and auditability. Storing policies in version control provides a single, authoritative source of truth. Every change is logged, making it easy to track policy evolution, understand current policies, and demonstrate compliance to auditors. This transparency builds trust and reduces the burden of compliance reporting. Reduced errors and improved security posture. Automating policy enforcement removes the potential for human error inherent in manual processes. PAC enables shift-left security, meaning policies are checked and enforced earlier in the development lifecycle, even during the code writing or infrastructure deployment phase. Catching policy violations before they reach production significantly reduces security risks and remediation costs. Scalability. As your digital footprint grows, so do the number of policies. PAC scales effortlessly. You don't need exponentially more humans to manage policies as your infrastructure grows. The automated systems handle the increased load. Better collaboration. Policy as code fosters collaboration between traditionally siloed teams: developers, security engineers, operations teams, and compliance officers. They can all contribute to, review, and understand policies using familiar tools and workflows, like Git repositories and CI/CD pipelines. Policy as code versus traditional methods. A quick contrast: hard-coded logic, simple initially but rigid, unmanageable at scale, and difficult to audit or change. PAC decouples and automates. Role-based access control, RBAC. Excellent for managing broad identity-based permissions, but limited when you need very specific, contextual decisions beyond who a user is, e.g. Can this particular user access this specific resource from this network at this time given these attributes? PAC provides the fine-grained control that augments RBAC. Manual documented policies, prone to misinterpretation, inconsistent enforcement, unscalable, and not verifiable by machine. PAC makes policies executable and verifiable. Open Policy Agent is the vital technology that makes policy as code a practical reality across diverse technical stacks. It provides the essential engine and the declarative language, Rego, that allows organizations to define, centralize, and consistently enforce policies at scale. OPA becomes the universal translator and enforcer of your digital rules, no matter where they apply. In the next chapter, we will pull back the curtain and explore OPA's architecture, its core components, and how it translates those abstract policy definitions into real-world decisions. Understanding OPA's internal workings will solidify our grasp on how it serves as the cornerstone of policy as code implementations. Chapter 3: Deconstructing OPA. How it works under the hood. In our exploration of policies and the paradigm of policy as code, we've established Open Policy Agent OPA as the core engine enabling this transformative approach. We've seen why policies matter more than ever and what policy as code entails. Now, it's time to pull back the curtain and understand how OPA actually functions. How does it take an input, evaluate it against a set of rules, and consistently deliver a decision? Let's return to our Department of Digital Rules and Decisions analogy. When a citizen, an application, or service needs a decision, for example, can new building plans be approved? They submit a request. This request isn't vague. It includes all relevant details: the type of building, its proposed location, the materials to be used, and the construction team applying for the permit. Much like this, OPA operates on precise inputs and well-defined rules. The core principle: decoupling decision from enforcement. Before we dive into the mechanics, it's crucial to reiterate OPA's fundamental principle. It decouples policy decision-making from policy enforcement. OPA doesn't directly stop an unauthorized user, block a risky deployment, or encrypt data. Instead, it acts as a highly knowledgeable consultant. It receives a query, consults its rulebooks, and provides a clear, unambiguous answer. The system that submitted the query is then responsible for taking action based on OPA's decision. This division of labor is precisely what makes OPA so versatile and broadly applicable across diverse systems. The OPA decision flow, a step-by-step walkthrough. When a system needs a policy decision, here's the typical life cycle within OPA. The request, input. An application, service, or infrastructure component forms a question in the form of a JSON, JavaScript object notation, document. This JSON input contains all the contextual information OPA needs to make a decision. For instance, if an API gateway needs to authorize a request, the input might include the user's ID, their authentication tokens, the API endpoint being accessed, the HTTP method, GET, POST, and any data included in the request body. The policies, Rego. OPA has preloaded policies, written in its native high-level declarative language called Rego. These policies are the actual rules. They define what conditions must be met for a certain outcome. For example, a Rego policy might look at the input and say, if the user is an administrator and the API endpoint is admin delete data, then the request is allowed. The contextual data, optional. Often, policies aren't just based on the immediate input. They might require additional context. OPA can load or query supplementary data. This data could be a list of allowed IP addresses, a directory of user roles, a configuration for an application, or even real-time information fetched from another service. For example, a policy might check if the user's location from the input is present in a list of approved countries from loaded data. The evaluation engine. This is the brain of OPA. When a request comes in, OPA's evaluation engine takes the input, the specified policies, and any relevant loaded data. It then processes the Rego code, applying its logic to the provided information. Because Rego is declarative, OPA efficiently determines all possible outcomes based on the rules. The decision, output. Finally, OPA returns a decision, typically as another JSON document. This output can be as simple as allow, true, or allow, false, or it can be more complex, providing reasons for a denial, a modified input, or a list of resources the user is allowed to access. The exact structure of the output is defined by the policy itself. Key components of an OPA deployment. To facilitate this decision-making process, OPA is typically deployed as a lightweight, standalone service. OPA as a daemon service. OPA commonly runs as a separate process, a daemon. This allows it to be independent of the applications it serves. It can be embedded within an application, run as a sidecar alongside a microservice, or execute as a host-level daemon, serving multiple applications on that machine. Each request to OPA is generally stateless, meaning OPA doesn't remember past requests, ensuring consistency. However, policies and static data can be loaded into OPA's memory for quick access. The policy engine. At the heart of OPA is its powerful policy evaluation engine, which interprets the Rego language. This engine is highly optimized for fast decision-making, capable of handling thousands of queries per second. The data API. OPA itself can store and manage data that policies might need. This data can be configured statically or updated dynamically from external sources. For instance, an OPA instance guarding Kubernetes might load cluster state data to make decisions about resource deployments. The decision API. This is the primary interface through which other systems communicate with OPA. It's typically a simple HTTP API endpoint where systems send their JSON input and receive a JSON output. Policy bundles and fetching. In real-world scenarios, policies and their associated data are not manually loaded. Instead, they are often packaged into bundles, compressed archives of policy and data files. OPA instances can be configured to periodically fetch these bundles from a remote server, like a cloud storage bucket or a Git repository, ensuring that all OPA instances have the latest policies. This mechanism is crucial for the version-controlled aspect of policy as code. Status and telemetry. OPA provides endpoints and mechanisms to report its health, policy evaluation metrics, and decision logs. These logs are vital for auditing and debugging, allowing you to trace exactly why a certain decision was made. Deployment models, where OPA runs. The flexibility of OPA's architecture means it can be deployed in several ways, depending on the latency requirements and management preferences. Sidecar model, often used with microservices and API gateways. An OPA instance runs alongside each application instance. The application sends requests directly to its local OPA, resulting in extremely low latency decisions. This distributes the policy decision-making. Host-level daemon. A single OPA instance runs on a server and is shared by multiple processes or applications running on that same host. This offers good performance for multiple applications on one machine. Centralized service. A cluster of OPA instances runs as a dedicated service, and all applications make network calls to this centralized policy decision point. While this might introduce slightly higher network latency, it simplifies central management of OPA instances, especially for organizations that prefer a consolidated policy platform. The choice of deployment model hinges on your specific use case, infrastructure, and performance needs. Regardless of how it's deployed, the fundamental process remains the same. Receive an input, evaluate against policies and data, and return a decision. So, when a new building plan in our digital city is submitted, the Department of Digital Rules and Decisions, OPA, receives the detailed plan, the input. It then consults its municipal code, the policies written in Rego, and its city records, loaded data like zoning maps or historic preservation lists. Within milliseconds, it produces a clear approved or denied decision, perhaps with a reason if denied. The building permit office, the enforcing system, then issues or denies the permit based on that precise ruling. Having deconstructed OPA's components and decision flow, the next logical step is to understand the language that brings these policies to life. In the following chapters, we will dive deep into Rego, OPA's policy language, exploring its syntax, logic, and how you can harness its power to define robust and intelligent policies for your digital operations. Chapter 4, Speaking Rego, The Language of Policy, Part 1, The Fundamentals. We've established OPA as your digital rulebook and policy, as code as the modern way to manage those rules. We've even peeked under OPA's hood to understand its mechanics. Now comes the exciting part, learning to speak to OPA. This means using Rego, Open Policy Agent's native policy language. Rego is the secret sauce that gives OPA its incredible power and flexibility. It's a high-level, declarative query language designed specifically for expressing policies. Unlike traditional programming languages that tell a computer how to do something step-by-step, imperative, Rego focuses on describing what the policy is, the conditions that must be true for a certain outcome. This declarative nature is a hallmark of policy as code and significantly simplifies policy writing and understanding. Think of Rego as the precise, unambiguous legal language used to write the laws of our digital city. These laws aren't vague suggestions. They are concrete statements about what is permitted or forbidden under specific circumstances. The anatomy of a Rego policy. A Rego policy typically consists of several key elements. Packages. Every Rego file starts with a package declaration. This organizes your policies into logical namespaces. It's like organizing your laws into chapters like traffic laws, building codes, or public safety. Package example auths. This line declares that all rules within this file belong to the example auths package. When OPA evaluates a query, it will ask for a decision from a specific package path. Rules. The core of any Rego policy is a rule. A rule defines a set of conditions that, if all true, cause the rule to succeed or be evaluated to true. Rules can define a simple Boolean status, like allow or deny, or they can generate data structures, like lists or objects. Let's start with a very basic allow rule. Package example auths. Default allow false hash by default, deny unless explicitly allowed. Allow, hash condition 1, check if the input method is get. Input method equals get hash equals is the equality operator. Hash condition 2, check if the input path starts with status. Starts with input path, status. In this example, default allow equals false is a default rule. This is a best practice in policy writing. It ensures that if no other allow rule evaluates to true, the default is to deny access. This is known as a fail-safe or deny by default approach. The allow block defines a rule. What's inside the curly braces are the conditions, often called expressions or statements. Input method equals get. This expression accesses a field called method within the special input variable, which holds the JSON data provided by the calling service, and checks if its value is exactly get. Starts with input path, status. This is a built-in function that checks if the path field of the input starts with the string status. For the allow rule to be true, meaning the action is allowed, both input method equals GT and starts with input path, status, must evaluate to true. If even one condition is false, the rule fails, and allow remains false due to our default. The input variable. As seen above, input is a magical, automatically available variable in every Rego policy. It always contains the JSON data that the requesting application sent to OPA for evaluation. This is how OPA gets the context for its decision. The user's role, the resource being accessed, the HTTP method, the time of day, etc. If our input JSON looked like this: method, get, path, status health, user, Alice, then input method would be get, input path would be status health, and input.user would be Alice. Data or data variable. Beyond input, policies often need to reference static or dynamic data that is loaded into OPA. This data is available under the data variable. For example, you might have a list of administrators or forbidden IP addresses. Imagine you load this JSON data into OPA. Users: Alice role admin, Bob's role viewer. Forbidden IPs 192.168.1.1, 10.0.0.5. Then in your Rego policy, you could refer to data.usersAlice role, which would be admin, or check if input source IP is present in data forbidden IPs. Understanding rules, a declarative approach. Rego is built on the concept of unification, which is similar to pattern matching. When you write allow condition, you're essentially saying, define allow such that condition is true. If condition can be satisfied, then allow becomes true. Consider another core aspect, multiple rules with the same name. This is where Rego shines. If you define a rule multiple times, OPA considers all definitions. If any of those definitions can be unified, i.e., if any set of conditions for a rule is met, then the rule is considered true. Let's refine our allow rule to include an admin path. Package example auths. Default allow equals false. Rule 1, allow get request to status paths. Allow, input method equals get. Starts with input path, status. Rule 2, allow post request to admin paths for admin users. Allow, input method equals post. Starts with input path, admin. Input.user equals data.users.alice.name hash, assuming data.users.alice.name holds Alice. Now if input method is GT and input path starts with status, the first allow rule makes allow true. Alternatively, if input method is post and input path starts with admin and input.user is Alice, the second allow rule also makes allow true. OPA doesn't stop after the first match. It evaluates all allow rules. If any of them are true, then the final allow decision is true. This makes it very easy to compose complex authorization logic by simply adding more rules that contribute to the overall allow decision. Basic data types and operators. Rego supports common data types, much like other programming languages. Strings, hello, world. Numbers, 1, 3.14. Booleans, true, false. Arrays or lists. Apples, banana, cherry. Objects or maps dictionaries. Name, Alice, age, 30. Null, null. It also provides standard operators. Equality, e.g., input method equals post. Inequality, e.g., input.user equals guest. Comparison, e.g., input temperature 90. Logical and implicit. Expressions within the same rule, separated by newlines or semicolons, are implicitly ANDed together. All must be true. Logical OR. While there is no explicit OR keyword, you achieve OR by defining multiple rules with the same head, as shown with our allow examples above. Putting it into practice. A simple access policy. Let's imagine a scenario where we want to allow access to anyone accessing paths under public, but only administrators can access internal paths. Our input might look like paths, v1, public data, user, Bob. Our data might contain administrators, Alice, Charlie, and our Rego policy, access Rego. Package playground, default allow equals false. Allow access to paths that start with public for anyone. Allow, input path 1 equals, public, hash check the second element of the path array. Allow access to paths that start with internal, only if the user is an admin. Allow, input path 1 equals, internal, hash check the second element of the path array. Administer hash, call the administer rule. Rule to determine if the user is an admin. Administer, some I hash, sum, is used to iterate over collections. User equals date administers I. Hash assign each element to variable user. User equals input.user hash check if the input user matches an admin user. In this example, we use input path 1 to access the second element of the path array. Remember, arrays are zero indexed. We define a subrule administer. This administer rule becomes true if the input.user matches any user found in data administers. The sum I keyword is crucial for iterating through arrays or objects in Rego. We'll delve deeper into sum in the next chapter. If the input path is v1, public, data, the first allow rule will make allow true regardless of the user. If the input path is v1, internal, secrets and input.user is Alice, then administer is true, and the second allow rule makes allow true. This basic foundation of packages, rules, inputs, and data is the bedrock of Rego. By understanding these core concepts, you've taken the first big leap into writing powerful and flexible policies. In Part 2 of Speaking Rego, we will build on this foundation, exploring more advanced constructs like iteration, functions, and comprehensive data manipulation that enable highly sophisticated policy logic. Chapter 5, Speaking Rego, The Language of Policy, Part 2, Advanced Constructs. In Chapter 4, we laid the groundwork for understanding Rego, OPA's policy language, by covering the fundamentals: packages, rules, the special input variable, and how to define simple conditions. We saw how Rego's declarative nature allows us to state what a policy should achieve, rather than how to execute it step by step. Now, let's build on that foundation and explore some of Rego's more advanced constructs that enable sophisticated and flexible policy definitions. These advanced features give Rego the power to deal with complex data structures, iterate over collections, and encapsulate reusable logic, making your policies not just functional, but also readable and maintainable. 1. Iteration with some. Policies often need to check a condition across a collection of items. For instance, is any user in this list an administrator? Or, does any of these requested resources contain sensitive data? In Rego, we use the sum keyword for this kind of iteration. Sum acts as an existential quantifier. It lets you establish a variable that will bind to elements within a collection, like an array or an object's keys values, allowing you to check conditions for those elements. Let's revisit our administr rule from Chapter 4, which checked if the input.user was present in a data list of administrators. Assume data administrs is Alice, Charlie. Administr, some I hash I, will iterate over the indices or keys of the collection. Input.user equals data administrs I. The sum I statement iterates through each element of data administrs via its index I. If at any point input.user matches data administrs I, the condition is met and administr rule becomes true. This is extremely powerful for checking membership or finding matching entries within lists or objects. A common pattern for some is defining variables during iteration. For example, to check if any requested action is forbidden for a user, assume input requested actions is read, write, delete. Assume data forbidden actions is delete. Deny, some action hash, action will take on values like read, write, delete. Action equals input requested actions, hash the underscore means any value for the index. Action equals data forbidden actions, hash check if action exists in forbidden actions. In this example, the deny rule will become true if any action from input requested actions, read, write, delete, is also found within data forbidden actions. 2. Custom functions, rules with arguments. Just like in other programming languages, you can define your own functions in Rego to encapsulate reusable logic. In Rego, these are essentially rules that take arguments. This enhances modularity, readability, and testability of your policies. Let's define a function that checks if a user belongs to a specific role. Assume data.userRoles equals Alice, admin, developer, Bob. Guest, user has role, username, required role. Sum I, role in data equals data.userRoles username. Role in data equals required role. Now, we can call this function from other rules. Allow, input method equals post, input path equals admin/config, user has role input.user, admin, hash calling our custom function. Using user has role makes the main allow rule much cleaner and immediately understandable. You can define as many such helper functions as needed. 3 sets for unordered collections. While arrays, lists, are ordered collections that can contain duplicate values, Rego also supports sets. Sets are unordered collections of unique values. They are represented using curly braces, with their elements listed inside. Sets are incredibly useful for operations like checking if an item is a member of a collection or finding common elements between 2 collections. Membership checking is very efficient with sets. Define a set of allowed countries. Allowed countries equals USA, Canada, Mexico. Deny, not input.user country in allowed countries. This deny rule becomes true if the input.user country is not found within the allowed countries set. For negation, not. The not keyword in Rego is used to express conditions that must not be true for a rule to succeed. It's essential for deny if not scenarios. Deny, not some approver approved hash deny, if no approver has approved. Some approver approved. Some approver. Approver equals input approvals. Approver status equals approved. In this example, the deny rule fires if the some approver approved rule cannot be made true. This is different from checking for false. It means the conditions for some approver approved are simply not met. 5. Comprehensions, building collections concisely. Rego offers comprehensions to create new collections, arrays, sets, or objects based on operations over existing collections. They are concise and powerful for data transformation within policies. Array comprehension creates a new array. Hash data.users equals id, 1 name, Alice, id, 2 name, Bob active. Vals, active usernames, equals user.name user, equals data.users. User active equals true. Hash result, active usernames would be Alice. This example reads as, create a list of user.name for every user in data.users, where user active is true. Set comprehension creates a new set. Hash input permissions, ready document 1, write document 2, execute script 1. All resources equals id permission equals input permissions. Document ID equals split permission. Hash result, all resources would be 1, 2. This creates a set of unique resource IDs extracted from permissions. Object comprehension creates a new object map. Hash data app configs name, app1 port 8080, name, app2 port 9090. App ports equals app.name, app port app equals data app configs. Hash result, app ports would be app1, 8080, app2, 9090. This creates an object mapping application, names to their ports. While understanding the full syntax might require a deeper dive, which can be done through OPA's official documentation and playgrounds, the conceptual idea is vital. Comprehensions allow you to transform and shape data within your policy in a very efficient and declarative way. 6. Useful built-in functions. Rego comes with a rich library of built-in functions for common tasks. We've seen starts with. Others include string manipulation, concat, trim, upper, lower, split format, collection operations, count, sort, reverse, sum, max, min, JSON interaction, JSON Marshal to convert Rego data to JSON string, JSON unmarshal to parse JSON string to Rego data, type checking, isString, isNumber, iSubject, etc. Comparison, maxmit, regular expressions, regexmatch, HTTP, HTTP send to make HTTP requests from inside a policy useful for fetching dynamic data. These built-in functions empower you to write sophisticated policies without reinventing the wheel for common operations. 7. Composing policies. Modularity is key. As policies grow in complexity, it's crucial to break them down into smaller, manageable, and reusable units. Rego's package system facilitates this. You can define policies in separate files, each with its own package. Then, from one policy file, you can reference rules defined in another package using its fully qualified name, e.g., data mylibraryauth sysadmin, user. This modular approach makes policies easier to understand, test independently, and maintain over time. It embraces the same best practices we use in software development for large applications. By mastering these advanced Rego constructs iteration, custom functions, sets, negation, and comprehensions, you gain the ability to write highly expressive, robust, and maintainable policies. You can effectively model intricate business logic, security requirements, and compliance mandates. Having now understood the fundamental building blocks of Rego and its more advanced capabilities, the next step is to see how OPA integrates into real-world systems to actually put these policies into action. Chapter 6, Integrating OPA, where policy meets your systems. We've now built a solid understanding of open policy agents, OPA, role, the power of policy as code, and the intricacies of the Rego language. But a policy engine, no matter how powerful, is only useful if it can seamlessly integrate with the systems it's meant to govern. This chapter explores precisely that, how OPA connects to, receives requests from, and provides decisions back to your diverse applications, infrastructure components, and microservices. Remember our Department of Digital Rules and Decisions, OPA. Its success depends on clear communication channels with all parts of the digital city. Without efficient ways for the building permit office, application, to submit a building plan, input, and receive an approval decision, the system breaks down. The beauty of OPA lies in its flexibility. Because it provides decisions via a simple API, often HTTP, it can be integrated at various points within your system architecture, from microservices to Kubernetes clusters, CI/CD pipelines, and even command line tools. The core integration pattern: request OPA decision enforcement. No matter the specific technology, the fundamental interaction pattern remains the same. System needs a decision. An application or service reaches a point where it requires a policy decision, e.g., is this user authorized to perform this action? Is this configuration compliant? Is this transaction risky? System crafts an input. The system marshals all relevant context into a JSON payload. This input contains all the data points the policy needs to make its call: user ID, resource ID, action, network details, time, attributes, etc. System queries OPA. The system sends this JSON input to an OPA instance. This is typically an HTTP post request to OPA's v1 data or v1 query API endpoint. OPA evaluates policy. OPA receives the input, retrieves the relevant policy, written in Rego, and combines it with any loaded data to produce a decision. OPA returns decision. OPA sends back a JSON response containing the policy's output, e.g., allow, true, decision, deny, reason, non-compliant configuration. System enforces decision. The originating system receives OPA's decision and takes appropriate action. If allow, false, it might return an access denied error to the user. If a configuration is non-compliant, it might block the deployment. Crucially, the enforcement logic remains within the original system. Common integration scenarios. Let's explore some prevalent ways OPA is integrated into modern technology stacks. 1. Microservices authorization. This is one of OPA's signature use cases. In a microservices architecture, dozens or hundreds of small, independent services communicate with each other. Each service needs to make authorization decisions. Is service A allowed to call service B with this data for user X? Integration. OPA is often deployed as a sidecar container alongside each microservice or as a daemon on the same host. When a request comes to a microservice, before it processes the request, it makes a local HTTP call to its co-located OPA instance. The input to OPA would include details like the incoming request's headers, payload, the user's identity, and the service being called. Benefits: extremely low latency, local network call, independent scaling of OPA instances with microservices, centralized policy management, policies are distributed to all OPA instances. 2. API gateway authorization. For services exposed via an API gateway, like Envoy, Kong, Apigee, or AWS API gateway, OPA can intercept and authorize incoming API requests before they even hit your backend services. Integration. The API gateway is configured to forward authorization requests to a centralized OPA instance or a cluster of OPA instances. The input would contain HTTP request attributes. OPA returns an allow/deny decision, and the gateway proceeds with routing the request or returns an error. Benefits: critical front door security, reducing load on backend services by blocking unauthorized requests early, consistent policy enforcement across all APIs managed by the gateway. 3. Kubernetes admission control, gatekeeper. Kubernetes is a highly dynamic environment. OPA plays a crucial role in ensuring that only compliant workloads and configurations are deployed. This is where OPA Gatekeeper comes in. Integration. Gatekeeper is a specialized implementation of OPA that leverages Kubernetes admission controller webhook mechanism. When users try to create, update, or delete resources in Kubernetes, like pods, deployments, or services, Kubernetes sends these requests to Gatekeeper. Gatekeeper uses OPA policies to evaluate the requests. For example, does this pod request privileged access? Are all containers using an approved image registry? Does this ingress have a hostname? If the request violates a policy, Gatekeeper rejects it, preventing the resource from being created or modified. Benefits: enforces security best practices, compliance, and operational governance from the very beginning of the deployment process. Shift left for infrastructure prevents misconfigurations from entering the cluster. 4. CI/CD pipeline checks. Policies aren't just for runtime enforcement. They can be integrated into your continuous integration, continuous delivery. CI/CD pipelines to shift left, security, and compliance validation. Integration. During the build or deployment phase, a CI/CD job can invoke OPA to evaluate infrastructure as code templates, Terraform, CloudFormation, container images, Docker files, or even application code against predefined policies. For example, before deploying a new cloud resource, OPA can check if it meets tagging requirements, security group rules, or data encryption standards. Benefits: catches policy violations early, reduces costly rework, ensures infrastructure and application deployments adhere to organizational standards before they go live, provides faster feedback to developers. 5. SSH access control. OPA can also authorize SSH access, ensuring only legitimate users can connect to specific machines or perform certain commands. Integration. The SSH daemon, SSHD, can be configured to call OPA for authorization decisions whenever a user attempts to log in. The input could include the username, source IP, public key, and target host. OPA decides if access is allowed. Benefits: fine-grained control over server access, dynamic policy updates without reconfiguring SSHD, centralized audit trail of SSH authorization attempts. 6. Database authorization. While databases have their own authorization mechanisms, OPA can add another layer of sophisticated, centralized policy enforcement, especially for complex, attribute-based access control, ABAC. Integration. An application typically sits between the user and the database. When a user queries data, the application first sends the query, along with user attributes, to OPA. OPA determines if the user is authorized to perform that specific query on that specific data. OPA might even recommend modifications to the query, e.g., filtering out sensitive rows before it hits the database. Benefits: unified policy for applications and data, granular control over data access beyond basic SQL permissions. The power of uniformity, a single policy language for many domains. The beauty of OPA and Rego is that you learn one language and implement one policy engine to cover a multitude of policy domains. Whether it's authorizing microservice calls, validating Kubernetes manifests, or checking CI/CD pipeline compliance, the core mechanism remains the same. This significantly reduces complexity, improves consistency, and accelerates policy development and deployment across your entire organization. OPA's flexible integration points and its declarative policy language empower you to embed policy decision-making precisely where it's needed, ensuring that your digital city operates under a single, coherent, and continually enforced set of digital rules. With this understanding of OPA's integration patterns, we can now turn our attention to one of its most impactful applications, securing the dynamic and complex world of Kubernetes, which we'll explore in the next chapter. Chapter 7, OPA and the Kubernetes ecosystem, Gatekeeper and beyond. If there's one environment where the principles of policy as code and the capabilities of open policy agent truly shine, it's Kubernetes. Kubernetes, the de facto standard for container orchestration, is inherently dynamic, distributed, and complex. Resources are created, modified, and deleted at a staggering pace, often by automated processes. Ensuring consistency, security, and compliance in such a rapidly evolving landscape is a monumental task, a task perfectly suited for OPA. Imagine our digital city now as a sprawling, self-managing construction site. That's Kubernetes. Developers are constantly trying to erect new buildings, deploying applications, pave new roads, creating network policies, and set up utilities, configuring secrets or storage. Without a central building inspector with clearly defined codes, this site would quickly descend into chaos, with insecure structures, misconfigured utilities, and unapproved designs. OPA, particularly through its specialized implementation, Gatekeeper, acts as this crucial building inspector, ensuring every new construction job adheres to the pre-approved digital building codes. The challenge: governing Kubernetes. Kubernetes provides powerful primitives for defining and managing workloads, but it doesn't intrinsically enforce many organizational policies. While it has role-based access control, RBAC, to manage who can access the Kubernetes API, RBAC often falls short when you need fine-grained control over what resources can be created or modified, how they are configured, or what data they can access. Consider these common Kubernetes challenges that benefit from policy enforcement. Security: preventing privileged containers, ensuring images come from approved registries, disallowing host port mappings. Resource governance: requiring resource limits requests for all pods, preventing oversized deployments, enforcing proper labeling for cost allocation. Compliance: ensuring data encryption at rest for storage volumes, mandating specific network egress rules, preventing public exposure of sensitive services. Operational best practices: enforcing consistent naming conventions, ensuring readiness/liveness probes are defined, disallowing deprecated API versions. Without a robust policy engine, developers might unintentionally deploy insecure configurations, or operations teams might struggle to ensure compliance across a large, dynamic cluster. This is precisely where OPA, especially through OPA Gatekeeper, comes into play. OPA Gatekeeper, the Kubernetes policy enforcer. OPA Gatekeeper is a specialized project that brings OPA's generalized policy enforcement capabilities directly into Kubernetes, leveraging Kubernetes' native admission controller mechanism. Admission controllers: Kubernetes gatekeepers. Kubernetes features admission controllers that intercept requests to the Kubernetes API server before an object is persisted. These controllers can mutate requests, change them, or validate them, reject them if they don't meet certain criteria. Gatekeeper is designed to be a validating admission webhook. How Gatekeeper works: request interception. A user or automated process sends a request to the Kubernetes API server, e.g., kubectl apply f-mypodyaml. Webhook call: the API server intercepts this request and, if configured, sends it to Gatekeeper's validating webhook. The entire resource manifest, the mypodyaml content, for example, is sent as JSON to Gatekeeper. Policy evaluation: Gatekeeper, which bundles an OPA instance, evaluates the incoming resource against a set of policies defined as constraint templates and enforced via constraints. Decision and enforcement: if the resource violates any active constraint, Gatekeeper sends a denial back to the API server, along with a descriptive violation message. The API server then rejects the request. If the resource passes all policies, Gatekeeper sends an approval, and the API server proceeds to create or update the resource. Constraint templates and constraints. Constraint templates, CRD. These are the Rego policies themselves. A constraint template defines rules about what constitutes a violation and what message to return. They are essentially reusable blueprints for policies. For example, a template might define the generic logic for no privileged containers. Constraints, CRD. These are instances of constraint templates. They activate a template by specifying where the policy applies, e.g., to which namespaces, specific labels, and any specific parameters. For example, a no privileged containers template can be instantiated as a disallow privileged containers in production namespace constraint. This separation allows policy logic to be reused across different scopes. OPA Gatekeeper in action: preventing privileged pods. Let's consider a common security best practice: preventing pods from running with privileged access, which gives them root capabilities on the host. Constraint template, Rego. A Rego policy would be written within a constraint template that checks if security context privileged is set to true on any container in a pod. Constraint, YAML. An administrator creates a constraint resource that instantiates this template, specifying that it applies to all pods in the default namespace. API version, constraints gatekeeper sh/v1 beta 1. Kind, K8's PSB no privileged. Metadata, name, pod privilege must be false. Spec match kinds, API groups. Kinds, pod. Namespaces, default. Parameters. Note, the actual Rego for this would be embedded in a separate constraint template resource that this K8's PSP no privileged constraint references. User action. A developer tries to deploy a pod in the default namespace with privileged. True. Gatekeeper intervenes. Kubernetes sends the pod manifest to Gatekeeper. Gatekeeper evaluates it against the active pod privileged must be false constraint. Rejection. Gatekeeper determines it's a violation and sends back an error. Admission webhook validation gatekeeper sh denied the request. Privileged containers are not allowed. The pod deployment fails. This entire process occurs transparently from the developer's perspective, who immediately receives concrete feedback about the policy violation, enabling them to shift left and correct their configuration earlier. Beyond Gatekeeper, other OPA integrations in Kubernetes. While Gatekeeper is the most prominent OPA integration in Kubernetes, OPA's flexibility extends to other areas. OPA as a sidecar for authorization. For applications running within Kubernetes, OPA can be deployed as a sidecar container in each pod. Your application queries its local OPA sidecar for specific authorization decisions, e.g., can this user access data customer records? This is excellent for microservice level authorization within the cluster. Network policy generation. OPA can be used to generate Kubernetes network policies based on higher-level organizational policies. Instead of manually writing complex YAML for network rules, you can define policies in Rego, e.g. Only front-end services can talk to back-end services on port 8080, and OPA generates the corresponding network policy resources. External data with OPA. OPA instances running within Kubernetes can dynamically load external data, e.g., user roles from an identity provider, threat intelligence feeds, asset tags from a cloud provider, to enrich policy decisions. This allows for even more context-aware and dynamic policies. The benefits of OPA in Kubernetes. Implementing OPA, and specifically Gatekeeper, in your Kubernetes environment offers immense advantages. Consistency. Enforces uniform security, compliance, and operational standards across all clusters, namespaces, and workloads. Automated governance. Eliminates manual checks, freeing up operations and security teams. Shift left, security. Catches misconfigurations and policy violations at deployment time, providing immediate feedback where it's most impactful. Dynamic policies. Policies can be updated and reevaluated on the fly without restarting pods or clusters. Auditability. Provides a clear, auditable trail of policy decisions and violations. Flexibility. Allows for highly granular and custom policies unmatched by built-in Kubernetes controls. Vendor neutrality. As a CNCF graduated project, OPA is open source and not tied to any single vendor or cloud provider. OPA transforms Kubernetes from a powerful but potentially chaotic orchestration platform into a tightly governed, compliant, and secure environment. By integrating OPA, organizations gain unprecedented control over their containerized workloads, ensuring that every building constructed in their digital city adheres to the highest standards. In the next chapter, we'll shift our focus from infrastructure governance to protecting the applications themselves, exploring how OPA secures microservice communication and API endpoints. Chapter 8. Securing microservices and APIs with OPA. In the world of modern software development, microservices and APIs are the backbone of almost every application. They enable agility, independent scaling, and continuous delivery. However, this architectural triumph introduces a significant security challenge. How do you consistently and effectively control access to hundreds or thousands of distributed services and their myriad API endpoints? Imagine our digital city again, but now it's populated by countless small, specialized shops, microservices, connected by a vast network of roads, APIs. Each shop offers specific services, and not everyone should have access to every service or every part of every service. A regular citizen shouldn't be able to access the city's financial records, and even a city planner should only access records relevant to their department. The challenge is ensuring that every interaction between these shops and their customers, users, or other services is properly authorized, without becoming a bottleneck or a source of security vulnerabilities. Traditional authorization methods, like hard-coding rules within each microservice or relying solely on coarse-grained role-based access control, RBAC, quickly break down in this environment. Hard-coded logic. Embedding distinct authorization logic in every microservice is a recipe for inconsistency, drift, and maintenance nightmares. A change in policy requires code modification, testing, and redeployment across potentially many services. Coarse-grained RBAC, while useful for initial authentication and broad role assignment, is this user an admin? Traditional RBAC often lacks the granularity needed for modern applications. It struggles with fine-grained, context-dependent decisions like, can this specific user view this particular document if they are part of this project and it's before the deadline? This is where Open Policy Agent OPA proves invaluable. OPA provides the perfect solution for externalized, context-aware authorization for microservices and APIs, acting as the consistent security guard at every shop store, all operating from a single, up-to-date rulebook. The power of externalized and attribute-based authorization. OPA's core value proposition for microservices and APIs is externalized authorization. Instead of each microservice attempting to codify its own access rules, it offloads that responsibility to a dedicated policy decision point OPA. This brings several key benefits. Centralized policy management. All authorization policies are written in Rego, managed centrally, typically in a version control system like Git, and distributed to OPA instances. This ensures consistency and simplifies auditing. Decoupling. Authorization logic is separate from business logic. Microservice developers can focus on their core domain, confident that authorization is handled by a specialized, external service. Fine-grained context. OPA excels at attribute-based access control, ABAC. Unlike RBAC, which largely relies on a user's role, ABAC considers a broader set of attributes about the user, e.g., name, department, security clearance, the resource, e.g., type, sensitivity, owner, the action, e.g., read, write, delete, and the environment, e.g., time of day, network location, device posture. This allows for highly nuanced and precise authorization decisions. For example, a user can read a sensitive document if they are in the legal department and it's during business hours, and their device is marked as compliant. Integration patterns for microservices and APIs. The patterns discussed in Chapter 6 are particularly relevant here. How a microservice or API integrates with OPA largely depends on its architecture and performance needs. OPA as a sidecar co-located daemon. How it works. This is arguably the most common and recommended pattern for microservices. An OPA instance runs as a lightweight co-located process, often in a separate container, known as a sidecar, alongside each microservice instance. When the microservice receives an API request, before processing it, it makes a local HTTP call to its dedicated sidecar OPA instance. The microservice sends the input, user details, requested action, resource path, etc., and OPA returns the allow-deny decision. Benefits: extremely low latency, local loopback call, high availability, OPA scales with the microservice, simple communication, and minimal impact on microservice code. The microservice code only needs to know how to form the JSON query and interpret OPA's JSON response. API gateway integration. How it works. For services exposed via an API gateway, e.g., Envoy, Kong, Apigee, OPA can sit at the gateway layer. The gateway intercepts all incoming API requests and forwards the relevant context, headers, path, method, JWT tokens, etc., to a centralized OPA cluster for an authorization decision. Based on OPA's response, the gateway either forwards the request to the backend microservice or rejects it. Benefits: enforces policies at the perimeter, preventing unauthorized requests from even reaching backend services. provides a consistent policy enforcement point for potentially many microservices downstream of the gateway, reduces load on backend services. Application-level OPA library SDK embedding, how it works. Less common for the full OPA engine, but a microservice could embed a lightweight OPA library or SDK directly within its code. This is suitable for very high-performance requirements, where even a local HTTP call to a sidecar is too much. However, managing OPA updates and policy distribution to many embedded libraries can be more complex than managing external sidecars. Benefits: zero network latency for policy decisions. Practical examples: crafting API authorization policies in Rego. Let's imagine a financial application with APIs for managing user accounts and transactions. Scenario 1: accessing your own account data. Policy goal: a user can only view their own account balance. OPA input comes from the microservices API handler, e.g., userid, Alice, request address or sonarid, Alice, action, read, path, accounts balance. Rego logic, package finance auths. Default allow equals false. Allow, input path equals accounts balance. Input action equals read. Input dot userid equals input request address or sonarid. This simple policy ensures that the user ID requesting the data matches the owner ID of the account being requested. Scenario 2: admin operations. Policy goal: only users with the admin role can access the admin API paths. OPA input, e.g., userid, Bob roles, user, admin, action, post, path. Admin/create user, Rego logic. Package finance auths. Import data roles assuming roles are loaded into OPA's data. Default allow equals false. Allow starts with input path, admin. Admin in input roles check if admin role is present in inputs roles array. Here, the API gateway or authentication service would typically enrich the input with roles information, which OPA then uses. Scenario 3: time-based restrictions/data filtering. Policy goal: customer support agents can only view customer data during business hours, 9 a.m. 5 p.m. Additionally, their view of sensitive data like account balance should be masked unless they have explicit approval. OPA input, userid, Charlie, roles, customer support, action, read, path. Customer's data, current time, 14:30. Rego logic, conceptual for data filtering. OPA can return not just allow deny, but also a transformed response. Package finance auths. Default allow equals false. Allow customer support during business hours. Allow customer support in input roles. Input current time equals 9:0. Input current time lesser equal 17:0. Modify the response if not explicitly approved. Response data, new data. Logic to filter or mask sensitive fields. For simplicity, if not approved, sensitive field is not input explicit approval. New data equals input requested data with sensitive field. In this case, the microservice would take OPA's response data and use it instead of the original data when returning to the client. This is a powerful advanced use case where OPA acts as a data transformer based on policy. Benefits of OPA for microservice/API security: consistency. All services speak the same authorization language, Rego, and consult the same policy engine, OPA, ensuring uniform enforcement. Agility and maintainability. Policy changes are managed centrally without code changes or redeployments to individual microservices. Reduced developer burden. Developers no longer need to write complex authorization logic within their services, allowing them to focus on core business features. Auditability. Every authorization decision can be logged by OPA, creating a clear and centralized audit trail for security and compliance. Scalability. OPA is designed for high performance and can scale independently of the microservices it protects. Future-proofing. As new authorization requirements emerge, they can be implemented in Rego and deployed without modifying application code. By integrating OPA into your microservice and API architecture, you empower your digital ecosystem with robust, consistent, and context-aware authorization. It allows your services to operate securely and independently, while maintaining a unified security posture across your entire digital city. Having explored how OPA integrates and secures various environments, our next chapter shifts focus to the practical aspects of building and maintaining these powerful policies. Testing, debugging, and best practices. Chapter 9, Building Robust Policies, Testing, Debugging, and Best Practices. We've explored the why, what, and how of OPA, dipping our toes into Rego and seeing how OPA integrates into various systems. Now, let's address a crucial aspect of any code, including policy as code, ensuring its quality. Just like application code, policies can have bugs, unintended consequences, or logical flaws. Building robust policies requires diligent testing, effective debugging, and adherence to established best practices. Think of our digital cities rulebook. It's not enough to simply write the laws. They must be meticulously reviewed for clarity, tested to ensure they produce the intended outcomes in various scenarios, and maintained with clear guidelines. A poorly written law, even with good intentions, can lead to confusion, injustice, or loopholes. The same applies to Rego policies. The importance of testing your policies. Because policies dictate permissions and behavior across critical systems, policy errors can have severe consequences. Unauthorized access, accidental data exposure, service outages, or compliance failures. Testing your policies thoroughly provides correctness, verifies that your policies behave as expected for valid inputs and produce the intended decisions. Reliability, ensures policies are resilient to unexpected or invalid inputs, preventing crashes or incorrect decisions. Completeness, helps identify edge cases or scenarios that might have been overlooked during policy writing. Maintainability, well-tested policies are easier to refactor, update, and extend as you have a safety net to catch regressions. Confidence, provides assurance that your policy system is working as intended, especially crucial for audit and compliance. Testing policies with OPA. OPA comes with built-in testing capabilities, allowing you to write unit tests for your Rego policies directly within the same files or in separate test files. Test rules. In Rego, tests are just special rules that start with test. A test rule typically contains an assertion that must be true for the test to pass. If the assertion is false, the test fails. Input and data. Within test rules, you can define specific input and data variables. These are local to the test and override the global input and data for that test's execution, allowing you to simulate different scenarios. Example test for an authorization policy. Let's imagine an example auths policy that allows GET requests to public paths and post requests to admin paths only for users with the role admin. Policy Rego. Package example auths. Default allow equals false. Allow GET to public paths. Allow. Input method equals get. Starts with input path, public. Allow post to admin paths for users with admin role. Allow. Input method equals post. Starts with input path, admin. Admin in input.user roles. Test cases. Test allow public get. Input equals. Method. Get. Paths public data. User, name, Charlie, roles, user. Allow with input as input hash use, with keyword to inject test input. Test in public post. Input equals. Method, post. Paths, public data. User, name, Charlie, roles, user. Not allow with input as input hash assert that allow should not be true. Test allow admin post. Input equals. Method, post. Paths, admin manage users. User, name, Alice, roles, admin. Allow with input as input. Test in an admin post. Input equals. Method, post. Path, admin manage users. User, name. Bob, roles, user. Not allow with input as input. Running tests. You run these tests using the OPA command line interface. OPA test policy Rego. OPA will execute each test rule and report whether it passed or failed. Continuous integration. Policy tests should be integrated into your CI/CD pipeline, just like application code tests. Any change to a policy should trigger the tests, and if they fail, the policy update should be blocked until the issues are resolved. Debugging policies. Despite careful testing, policies can sometimes behave unexpectedly. OPA provides several tools to help debug your policies. OPA Playground. an invaluable online tool provided by Styra, the creators of OPA, that allows you to paste your Rego policy, provide an input, and see the exact output. It highlights syntax errors and allows for quick iteration. OPA eval command. The OPA eval command line tool is your local policy sandbox. OPA eval I input JSON data policy allow evaluates the allow rule of policy Rego with input JSON. OPA eval explain data policy allow I input JSON. This is extremely powerful. The explain flag shows you a detailed trace of how OPA evaluated the policy, including which rules were tried, which conditions succeeded or failed, and why. This is like stepping through your code line by line. OPA eval data policy allow pretty prints the output, making it easier to read. Decision logging. Configure your OPA instances to log full decision records, the input, the policy evaluated, and the output. These logs are crucial for understanding real-world policy, behavior, and diagnosing issues in production. Integrate these logs with your centralized logging and monitoring solutions. Best practices for writing Rego policies. Beyond testing and debugging, adopting sound best practices is essential for creating high-quality, maintainable, and robust Rego policies. Deny by default, fail-safe. Always start with a default rule that denies access or prevents an action. This ensures that if no specific allow or permit rule is met, the system defaults to the safest state. Default allow equals false. Hash or if returning more complex output, default response equals allowed. False, reason, no policy matched. Modularity with packages. Break down complex policies into smaller, logical packages. Each package should encapsulate a specific domain or set of related rules. This improves readability, reusability, and makes policies easier to test independently. Package myopositive 1. Package myopoth deep access. Package myop validation Kubernetes. Clear naming conventions. Use descriptive and consistent naming for packages, rules, and variables. This significantly improves policy readability and understanding. For a rule named allow, input path access is more descriptive than IPA. Comments. Document your policies thoroughly. Explain the purpose of a package, the logic behind complex rules, and any non-obvious design choices. Future you and your teammates will thank you. Small, focused rules. Avoid monolithic rules with too many conditions. Break them into smaller, reusable helper rules. This makes policies easier to understand, test, and debug. Hash good. Allow. Userize admin. Resources public. Userize admin. Hash bad too much in one rule. Allow. Input.userrole equals admin. Input path equals public data. Immutable inputs. Think of the input as immutable. You shouldn't try to change it within your policy. Policies consume input to produce decisions, they don't modify it. Handle missing data gracefully. Policies should be resilient to missing or unexpected data in the input or data variables. Use features like the default keyword for variables or check for existence using if with an assignment, some var if var. Avoid crashes due to null or missing fields. Leverage helper functions. For common logic or complex computations, create helper rules that take arguments, as discussed in Chapter 5. This promotes reusability and reduces duplication. Attribute-based is preferable to role-based. While you can implement RBAC in OPA, leveraging attributes, ABAC, about users, resources, and environment often leads to more flexible, scalable, and future-proof policies. Instead of just is user an admin, consider is user's department finance and is the data confidential. 10. Regular review. Treat policies like critical infrastructure. Conduct regular peer reviews and security audits of your policies. As your systems evolve, so should your policies. Building robust policies is an ongoing process of design, implementation, testing, and refinement. By embracing the testing capabilities of OPA, utilizing its debugging tools, and adhering to established best practices, you can ensure that your digital rulebook is not just comprehensive, but also accurate, reliable, and secure. Having gained practical skills in policy creation, debugging, and quality assurance, we're now ready to look at how OPA is being utilized in the real world across various organizations, which will be the focus of our next chapter. Chapter 10, OPA in the Wild, Real-World Case Studies. Theory is essential, but seeing how Open Policy Agent OPA is applied in real-world scenarios brings its power and versatility to life. From startups to large enterprises, OPA has become a critical component in solving complex policy challenges across diverse industries. These case studies illustrate the broad applicability of policy as code and offer insights into best practices and the tangible benefits of adopting OPA. Imagine our digital city now with various successful enterprises, each with unique needs, but all benefiting from a unified, efficient system of rules. Whether it's a nimble tech company ensuring agile deployments, a financial institution meeting stringent compliance, or a utility provider securing critical infrastructure, OPA helps them thrive. Case Study 1. Financial Services Centralized Authorization for Regulated Environments. Organization Type: Large, globally distributed financial institution. Challenge: Financial institutions operate under immense regulatory scrutiny, e.g., GDPR, PCI DSS, SOX, bespoke financial regulations. They deal with vast amounts of sensitive customer data and need highly granular access controls for thousands of applications and services. Traditional, per-application authorization logic was inconsistent, difficult to audit, and created significant compliance overhead. Manual audits were slow, expensive, and prone to human error, especially across disparate systems. OPA Solution: The institution adopted OPA as its centralized authorization policy engine. Unified Policy Store: All security and compliance policies, e.g., only a specific team can view high-value transactions, no access to customer PII from outside the corporate network. All data access must be logged, were translated into Rego and stored in a central Git repository. API Gateway Integration: OPA was integrated with their API gateways to perform real-time authorization for hundreds of internal and external APIs. Every API request was first validated by OPA, which made decisions based on user roles, transaction types, data sensitivity, and network location. Microservice sidecars: For critical backend microservices, OPA was deployed as a sidecar, allowing for fine-grained authorization decisions within the service mesh. CI/CD pipeline integration: Policies were also used in CI/CD pipelines to validate infrastructure as code, e.g., ensuring cloud storage buckets are encrypted and not publicly accessible, and application configurations. Benefits: Enhanced compliance and auditability. A single source of truth for all authorization policies drastically simplified regulatory audits. Every decision point could provide clear logs of OPA's determination, fulfilling audit requirements. Reduced risk and improved security posture. Consistent enforcement across all layers reduced the risk of unauthorized data access and improved the overall security of sensitive financial data. Increased agility. Policy changes no longer required application code changes or redeployments, significantly accelerating the pace of development and compliance updates. Case Study 2. Cloud-native SaaS provider developer enablement and cloud governance. Organization type: Fast-growing software as a service, SaaS, company leveraging multi-cloud Kubernetes environments. Challenge: As the company scaled, cross-functional teams provisioned cloud resources and deployed applications independently. This led to cloud sprawl, inconsistent security configurations, and difficulty enforcing cost optimization and security best practices. Developers were inadvertently deploying non-compliant resources, which were caught late in the cycle, leading to rework and slowing down delivery. OPA Solution: OPA was implemented primarily for cloud resource governance and Kubernetes admission control. OPA Gatekeeper: Deployed across all Kubernetes clusters to enforce corporate policies such as all pods must have resource limits defined, no privileged containers, images must originate from the approved container registry, and only specific teams can deploy to production namespaces. Terraform Cloud Formation Policy Enforcement: OPA integrated into their CI/CD pipelines to validate Terraform infrastructure as code plans before resources were provisioned. Policies checked for things like all S3 buckets must be encrypted by default, no public IP addresses on EC2 instances, or Tags for cost center and owner are mandatory for all resources. Automated remediation, planned. Some policies moved towards audit and notify initially, with plans for auto-remediation, e.g., automatically encrypting unencrypted buckets. Benefits: shift-left governance. Developers received immediate feedback during the development and deployment phases, preventing non-compliant infrastructure from ever being provisioned. This drastically reduced friction between development and operations security teams. Cost optimization. Enforcing resource limits and mandatory tagging help them manage and attribute cloud costs more effectively. Accelerated development. By embedding automated policy checks, the development teams could innovate faster, with the confidence that their deployments were compliant. Standardization. Enforced consistent naming, tagging, and security postures across a sprawling multi-cloud footprint. Case Study 3. Utility provider securing critical infrastructure, SCADA ICS. Organization type. Large public utility responsible for water and energy supply, with a mix of legacy and modern systems, including SCADA, supervisory control and data acquisition, and ICS, industrial control systems. Challenge. Legacy SCADA environments are notoriously difficult to secure and typically use highly specialized, often proprietary, access control mechanisms. Modernizing these systems while maintaining extreme levels of security and operational integrity was a major hurdle. Compliance with critical infrastructure regulations was paramount. They needed a unified way to control access to operational technology, OT systems from information technology, IT systems, and vice versa. OPA solution, a hybrid approach using OPA for both IT and OT access control. Centralized policy engine. OPA runs in a hardened Kubernetes cluster, acting as a central policy decision point for various access requests. Custom integrations. Developed custom connectors to integrate OPA with their industrial control systems gateways. When IT personnel attempted to access an OT system, the request would first go to OPA. The input included details about the user, their role, the specific OT device they wanted to access, the time of day, and source IP. Location-based access. Policies factored in physical location and network segmentation. For example, only engineers physically present in Control Room A can send commands to Substation 1 during scheduled maintenance windows. Emergency overrides. Policies also included provisions for pre-approved emergency override procedures, where specific individuals could bypass certain controls under tightly audited conditions. Benefits. Enhanced operational security. Drastically improved the security posture of critical infrastructure by centralizing and standardizing access control, replacing disparate and often insecure legacy methods. Regulatory compliance. Met stringent industry regulations for access to critical infrastructure, providing clear audit trails for every access attempt to OT systems. Harmonized IT-OT security. Bridged the traditional security gap between IT and OT, creating a more unified and manageable security framework. These case studies represent just a fraction of OPA's diverse applications. They demonstrate that OPA is not just a theoretical concept. It's a practical, production-ready solution for organizations striving for agility, security, and compliance in increasingly complex digital environments. The common thread is OPA's ability to provide a flexible, unified, and automated approach to policy enforcement, regardless of the underlying systems. As organizations continue to embrace cloud-native architectures and distributed systems, the need for robust policy as code solutions like OPA will only grow. In our final chapters, we'll look at the broader OPA ecosystem, its future trajectory, and summarize how OPA empowers organizations to build truly resilient and governed digital operations. Chapter 11. OPA Ecosystem and the Road Ahead. We've journeyed from understanding the fundamental need for policy in the digital age, through the transformative concept of policy as code, to the practical mechanics of OPA and its real-world applications. Now, it's time to broaden our view and consider OPA within its larger context. The vibrant ecosystem of tools, projects, and communities that surround it, and what the future might hold for this powerful technology. OPA's strength is not just in its core engine, but also in the extensive community and array of integrations that have sprung up around it. As a graduated project of the Cloud Native Computing Foundation, CNCF, OPA enjoys widespread adoption and contributions from leading technology companies and a dedicated open-source community, ensuring its continued evolution and stability. Key components of the OPA ecosystem. OPA Gatekeeper. We've already explored Gatekeeper's role in Kubernetes. As the dedicated project for Kubernetes admission control, it's fundamental to cloud-native governance, providing custom resources for defining constraint templates, the Rego policies, and constraints, instances of policies applied to specific parts of a cluster. Gatekeeper is often the entry point for many organizations leveraging OPA. External Data Providers (EDP). Gatekeeper is expanding its capabilities to allow policies to pull external data, e.g., from a CMDB, an identity provider, or a vulnerability scanner, to make richer, more dynamic decisions. External integrations and plugins. OPA's lightweight nature and simple HTTP API make it incredibly easy to embed or integrate into virtually any system. This has led to a proliferation of integrations. API gateways, Envoy, Istio with Mixer/Envoy Filter, Kong, AWS API Gateway, Apigee. These leverage OPA for centralized API authorization. Service meshes. Istio and Linkerd can integrate OPA for fine-grained authorization within the service mesh, controlling service-to-service communication. Infrastructure as Code, ISC tools. Sentinel, HashiCorp's proprietary policy engine for Terraform, is one, but OPA is gaining traction via its CLI, OPA Eval, for validating Terraform plans, CloudFormation templates, and ARM templates during CI/CD. Databases. Plugins are emerging to allow OPA policies to control access to specific rows or columns in databases. Identity and Access Management, IAM systems. OPA can enrich decisions from traditional IAM systems, providing fine-grained authorization beyond roles. Community and learning resources. OPA documentation. Comprehensive and well-maintained official documentation with examples and guides. OPA Slack channel, an active community forum for asking questions, sharing knowledge, and getting support. Styra Academy. Free online courses and resources provided by Styra, the company founded by OPA's creators, offering structured learning paths. Community blog posts and tutorials. A wealth of community-contributed content showcasing diverse use cases and practical implementations. O'Reilly books and online courses. Various external resources from expert authors on OPA and policy as code. Tooling and ecosystem extensions. VS Code extension provides syntax highlighting, linting, and other IDE features for Rego. Rego playgrounds, online tools like the OPA playground mentioned in Chapter 9 for rapid prototyping and testing of Rego policies. Confdest, a utility built on OPA that allows you to write policies for arbitrary configuration files, YAML, JSON, INI, TOML, Docker files. It's great for validating configurations in CI/CD pipelines. Policy bundles, mechanisms for packaging policies and distributing them efficiently to OPA instances. The road ahead, evolution and future directions. OPA is a mature, graduated CNCF project, but its development is far from static. The community continues to innovate, expand its capabilities, and address emerging challenges in policy enforcement. Enhanced policy distribution and management. As organizations manage hundreds or thousands of policies, efficient distribution, versioning, and lifecycle management become critical. Expect continued improvements in tools and methodologies for large-scale policy deployment. Observability and auditing. While OPA provides decision logging, the focus will continue to be on deeper integration with observability stacks, tracing, metrics, centralized logging, to provide granular insights into policy decisions, performance, and violations. Ensuring complete auditability is paramount for compliance and security. Policy as a service, PaaS. More vendors are likely to offer OPA as a service platforms, simplifying the deployment and management of OPA instances and offering advanced features like policy analytics and compliance dashboards. DAS is a leading example in this space. Beyond authorization, while authorization is OPA's primary use case, its declarative nature makes it suitable for a broader range of policy domains. Expect to see more creative applications in data governance, data masking filtering, network segmentation, configuration management, and even business process orchestration. Performance optimizations. Continued work on optimizing the Rego evaluation engine for even lower latency and higher throughput, especially for large policy sets and complex data inputs. Decision as a service paradigm. OPA solidifies the pattern where applications offload complex decision-making to a specialized external engine. This separation of concerns will likely proliferate beyond security policies to other business rule engines. Easier policy authoring. While Rego is powerful, it has a learning curve. Efforts may be made to provide higher-level abstractions or visual tools that simplify the creation of common policy patterns, making OPA more accessible to a broader audience, including compliance and governance teams. Edge and IoT policy enforcement. As computing moves to the edge, there's a growing need for local, real-time policy enforcement for IoT devices or edge gateways. OPA's lightweight footprint makes it an ideal candidate for these environments. Integration with AI/ML. Policies could potentially be informed or generated using AI/ML insights, while OPA would provide the transparent, auditable enforcement layer for these algorithmic decisions. Contributing to OPA. For those inspired by OPA's capabilities, the OPA project is open source and welcomes contributions. Whether it's contributing to the core Rego language, improving documentation, building new integrations, or providing examples and use cases, there are many ways to get involved and shape the future of policy as code. The OPA ecosystem is a testament to the power of open source and a vibrant community. Its continued growth signifies a broader recognition that policy enforcement is a critical, foundational layer in modern computing, on par with identity, networking, and storage. By understanding this ecosystem and looking towards its future, we can better position ourselves to harness the full potential of OPA in our own digital operations. In the final chapter, we will summarize the transformative impact of policy as code and OPA and offer a concluding vision for empowering your digital operations. Chapter 12. Conclusion. Empowering your digital operations with policy as code. We have reached the end of our journey through the world of Open Policy Agent and the paradigm of policy as code. We began by acknowledging the escalating complexity of our digital world, an environment where traditional methods of managing rules and behaviors through hard-coded logic, manual processes, or coarse-grained access controls simply fall short. This complexity often leads to security vulnerabilities, compliance gaps, operational inconsistencies, and a bottleneck on innovation. We then introduced the visionary concept of policy as code, PAC, a transformative shift that treats policies as executable definitions. By translating rules into machine-readable declarative languages like Rego and managing them with the same rigor as application code, via version control, automated testing, and CI/CD pipelines, PAC delivers unprecedented consistency, agility, and auditability. It liberates organizations from manual drudgery and human error, enabling a shift-left approach to governance where problems are caught early and often. At the heart of this transformation lies Open Policy Agent OPA. We deconstructed OPA, understanding its role as a universal policy decision engine decoupled from enforcement. This decoupling gives OPA its remarkable versatility, allowing it to provide authorization decisions, validate configurations, and enforce governance across a dizzying array of systems. We've meticulously explored Rego, OPA's powerful declarative language, from its fundamental building blocks to its advanced constructs, demonstrating its ability to express highly nuanced and context-aware policies. The real strength of OPA, however, lies in its seamless integration points. We've seen how OPA plugs into critical components of modern architectures, securing microservices and APIs, providing fine-grained, attribute-based authorization at the service and API gateway layers, ending the nightmare of distributed, inconsistent access controls. Governing Kubernetes. Through OPA Gatekeeper, ensuring that containerized workloads and cluster configurations adhere to security best practices and compliance mandates, preventing misconfigurations before they manifest. Enhancing CI/CD pipelines, embedding policy checks early in the development lifecycle, empowering developers with immediate feedback, and preventing non-compliant deployments. Beyond, covering a wide range of use cases from SSH access control to database authorization, showcasing OPA's adaptability across the technology stack. Crucially, OPA empowers organizations to speak one language of policy, Rego, across all these diverse systems. This uniformity simplifies policy management, reduces specialized knowledge silos, and fosters a more collaborative environment between development, security, and operations teams. It is a unifying force in an increasingly fragmented digital landscape. Our journey concluded by showcasing OPA's profound impact through real-world case studies. From the stringent regulatory demands of financial services to the rapid development cycles of SaaS providers and the critical infrastructure protection of utility companies. These stories underscore that OPA is not just a theoretical concept. It is a proven, battle-tested solution that delivers tangible benefits. Enhanced security postures, streamlined compliance, accelerated development cycles, and superior operational governance. The future is governed by code. The trend towards policy as code is not a passing fad. It is a fundamental shift in how organizations manage risk, ensure compliance, and enable innovation in a digital-first world. As our systems become even more distributed, dynamic, and automated, the need for intelligent, automated policy enforcement will only intensify. OPA, as a leading open-source standard, is perfectly positioned to meet this demand. By adopting OPA, you are not just implementing a piece of software. You are investing in a philosophy that champions transparency, automation, and consistency in policy management. You are transforming your digital rulebook from a static, cumbersome impediment into a dynamic, agile enabler. You are empowering your teams to move faster, more securely, and with greater confidence. The era of policies being afterthoughts or manual bottlenecks is drawing to a close. The future is one where policies are treated as first-class citizens, managed as code, and enforced by intelligent engines like OPA. Embrace policy as code. Unlock the power of OPA. Empower your digital operations for the challenges and opportunities of tomorrow.